Allow me to introduce our next speaker, Dr. Jeff Zweerink. Astrophysicist Dr. Jeff Zweerink is a senior research scholar at Reasons to Believe. He earned his PhD in astrophysics from Iowa State University. His writing and speaking encourage people to consider the connection between Scripture's truth and scientific evidence. He is the author of Escaping the Beginning, Is There Life Out There? And Who's Afraid of the Multiverse? He is also co-author of Building Bridges and the Impact Events Student Devotional Series. Jeff is also a project scientist at UCLA. Please join me now as we enjoy Jeff's presentation.
Now, just to kind of get a little bit of feel for it, is as my understanding of it is, you've got this instrument that is meters across, that is optical quality mirrors, that folds up into a rocket. We launch off into space, and then as it's traveling across the harsh realities of space, it will unfold itself into a place where you get incredible quality images. And it does so in such a way that it goes out about 1 million miles away from the Earth. It's now in a place where part of what you have to do to get the images that James Webb does is that it needs to be really, really cold. And so you've got two really immense sources of heat. You've got the Earth and you've got the sun. And it turns out there's this place that where if you line the sun and the Earth up, there's a spot on the other side where you can orbit something and it always stays there. And so we launch it out to that spot, and we unfurl this big shield that's about the size of this room, and it does all of this autonomously on its own. There's no place where we get up there, it's like, oh, it didn't quite work here, go out there and push that around, or try it again. It just works. And it works in such a way that if you're on the sun side of the shield, I believe the temperatures are hot enough you could boil water, but on the back side of the shield, you're a stone's throw away from about the coldest temperatures in the universe. It's just a phenomenal technological accomplishment. A lot of scientists love to sit in and work with the equations and figure out what it says. I like to build stuff. That's my interest in science. Most of the things I've worked on have been, what can we build to get the data out we want? And I look at what James Webb does and I'm like, that's really, really cool. And so we get to see all of these pictures, but the reality, yeah, it's cool in two ways. That's right, I like that. We have to live in a certain kind of universe that allows that to happen. We have to live in a universe that works to exacting specifications. I mean, you think all the little steps we have to do, they have to work precisely, reliably, consistently. And James Webb has, and the engineers and the scientists and everybody who's built that has engineered it, understanding, have tamed the universe to make it work. And I see a reflection of that in Genesis 1, to be fruitful and multiply, fill the earth, rule over it and subdue it. We have subdued creation in some sense to build this instrument that allows us to see what's going on in the universe. Now, I'm supposed to talk about the cosmological implications, past and future, of the James Webb. And so to do that, we kind of need at least a little bit of picture of what does cosmology say? What do we know about the universe? And probably the simplest summary I could get is the universe began, and we're now here looking at it. Now, there's a lot of details I've kind of glossed over there. I realize that. But I thought, okay, well, that's not going to work. Let's go a little bit deal. So, okay, the whole universe started in this hot, dense state, and then about 14 billion years ago, expansion started. The Earth, it began to cool. The autotrophs, they began to drool. We built a wall. We built a great pyramid. We got math. We got science. We got history. It's unraveling the mystery that all started with the Big Bang. And if you'll pardon the reference back to a very popular TV show, actually gives a reasonable summary of what we've got going on there. But in order to ask the question, what are the cosmological implications, we need to have a framework of how do we actually think about the universe. And as it stands today, that is inflationary Big Bang cosmology. Now, there are other ideas out there, but this is kind of the way the scientific community thinks about the universe. And so I think it's relevant to just kind of spend some time talking about what does inflationary Big Bang cosmology say, because without that picture, it's hard to know what does the James Webb Space Telescope bring to our understanding. Other than that, it's just some really fascinating, cool pictures that are hard to interpret if we don't have a framework for interpreting them. And so this is the framework that the scientific community is operating in. And I want to break up inflationary Big Bang kind of into 3 periods, that being the period up to about 10 to the minus 11 seconds, and that may seem arbitrary, but it's not, because this is the region where we've explored theoretically. You know, we can talk about inflation and how does that work, and vacuum, false vacuum, and what, things. We can talk about grand unified theories. We can talk about the theory of everything. We can talk about supersymmetry. And there are tools we have theoretically to go in and explore what's going on in this era and how might it have worked and what could we say. And then if we go from 10 to the minus 11 seconds, maybe up to about 380,000, maybe 400,000 years ago, we've got now this region where we've explored with observations. We can talk about electroweak theory, Big Bang nucleosynthesis, the cosmic microwave background radiation, and I'll kind of hit on some of those things here in a minute. And then from there, we can talk about 380,000 years till now. And this has been explored with telescopes, but there are some rather significant gaps in there. You know, where I kind of glossed over some of the details. You'll find that there are some places in cosmology where we've kind of glossed over some of the details. And the bottom line is the James Webb Space Telescope is built to allow us to peer in and see some of those details. So I'm going to highlight where that is. You know, David just showed this picture, and I think it's a pretty good and accurate picture. It's a nice summary of what we know about the universe. So we start out, we're off on the right. The inflations, the beginnings of the universe are way off on the left. And if you go let's go from the right and go back, because that's kind of how it started. Our current picture of cosmology is that as people were using telescopes, I mean, Vespo Slifer was noticing that you've got these objects that you're looking at where the spectral lines we expect are shifted to different wavelengths, and it looks like they're moving in some sense. And Edwin Hubble was able to do some observations and show that you could actually put distances on those things. And as you mapped out the redshift or the velocity versus distance, what lo and behold, what was found is that the farther away an object was, the faster it was moving away from us. And that's a telltale signature of an expanding universe. And so that was started, kind of in the early 1900s, not too long after Einstein published his seminal work on general relativity, where when you get down and you look at the equations of general relativity, what you find is that the generic descriptions or the generic solutions either have the universe expanding or contracting. And it's a fun argument or discussion to go look and see, how did that play out in terms of how Einstein dealt with that reality that his equations predicted either an expanding or collapsing universe until 15-ish years ago. From there, eventually we found that lo and behold, we find signatures of a universe that is expanding. And if the universe is expanding, the question is, what's it expanding into? And if you expand it backward, or if you contract as it goes backwards, what happens with that? And there were numbers of theories ideas of how the universe behaved in those intervening years, the 1920s up to about the late 1960s, early 70s. And ultimately, with the discovery of the cosmic microwave background radiation, where somebody took a new instrument, looked out into the heavens in a way they hadn't looked before, and they found this pervasive cosmic microwave background radiation. And ultimately, after some validating that the results actually were correct and doing some theoretical work, it said, okay, this expansion, that the farther away a galaxy is, the faster it's moving away from us, coupled with this cosmic microwave background radiation, said that, Big Bang type universes, those are the ones that really seem to work. That's the kind of universe in which we live. And so that all happened really before almost on the time scale of when I was born. So this is all stuff that I didn't even get to witness, but I live and have grown up in an era where this is our prevailing picture of the cosmos. And in that, you've got galaxies that are developing. You go back, there's these dark ages. If you go back and you push back way back into that earlier period, that's the part that really excited me, because that's what was going on when I was growing up. Because you've got the cosmic microwave background radiation, and we now see it as these ripples in there, but originally it was just this very uniform radio emission that was a sign that we lived in a very homogeneous universe. And that was a marker of this is what the universe looked like at one point in time. And then what happened before that? And before that, you now have to get to higher energies and higher temperatures. And so we began probing back into that era. And so this kind of makes it look like, I mean, if you look at it here, this is kind of laid out in terms of time. Not quite exactly, but you got most of the universe is galaxies forming, and we know that there's a black hole at the center of our galaxy because we built instruments that allow us to see stars going around the center, and there's nothing there in the center we can see, and there's about a 400 million solar mass black hole. 400 or 4 million? 4 million. That's what I thought. It was 4 million, sorry. We just find all these spectacular, fascinating things about the universe and how galaxies interact and all this sort of stuff. But it makes it kind of look like that's been the dominant picture. But when you look at scientifically, a lot of things tend to happen not linearly with time, but logarithmically with time. So if we kind of plot it a little bit different, again, this isn't quite logarithmic with time, what you see is that all of the stuff with the stars and galaxies, that's really kind of just off in one little section. There's a whole lot of interesting stuff that happens in between there. And among the things that we can say is, all right, we know that the universe is expanding, so what happens if it contracts? Well, if you take something and you contract it, it heats up. And so scientists were asking the question, as the universe heats up, as you go backwards in time, what sorts of things happen? Well, it turns out as you get down into about the first 3 or 4 minutes, our universe has a density and temperature similar to the interior of stars. And so you actually get hydrogen fusing into helium. Or if you run it backwards in time, you get helium breaking up and all becoming hydrogen. But that's not as interesting because we actually know it goes the other way. And so we know that when we look at our universe, we see that it's about 75% hydrogen, 25% helium, and that is a result of what's happening in this first 1 second to about 4 minutes of the universe, where it's in this stage where nuclear fusion can happen. And one of the telltale signatures, or why we think Big Bang cosmology is right, is that in this era, not only does hydrogen fuse into helium, but a little bit of lithium and a little bit of beryllium is produced, and some deuterons, which are, you take a proton and you add a neutron to it, and that's a deuteron. And so we can actually calculate, given the cosmic microwave background radiation gives us a stamp of the temperature, and then as you run it back, at some point it's going to be hot enough, and you can calculate how much hydrogen should be there, how much helium should be there, how much lithium, beryllium. And lo and behold, we can go out and make those calculations, and when we go measure those quantities in the universe, it turns out they line up very well. So we got this measurement that Big Bang cosmology is a good description of the universe. And as we keep pushing further back, you got to build some more powerful tools. So we can build particle accelerators that allow us to look at the 4 fundamental forces: the electromagnetic force, the weak force, the strong force, and the gravitational force. And oddly enough, when we do that, it turns out that these 2 forces, you take the electromagnetic force and the weak nuclear force, these things that look incredibly different, because the electromagnetic force operates across the entire universe. A photon that's here can travel all the way across the universe, whereas the weak nuclear force operates on a very, very small distance. And electromagnetism works on charged particles, whereas the weak nuclear force kind of works on things decaying. It's a really difficult force to describe in that sense. But why I chose that 10 to 11 time is that as scientists are looking at this, they said, wait a second, we know things have mass in the universe. And there's this symmetry that goes on where if things are hot enough, you've got a symmetry between these four particles, but as the universe will cool down, the symmetry between those particles will split and you'll get a photon, which is massless, and you'll get a W particle that's both one positive, one negatively charged, and a Z particle. And those particles work out so that the photon mediates the electromagnetic force, and the W and Z bosons would mediate the weak nuclear force. And we build particle accelerators and show, lo and behold, these particles actually exist. And numbers of years later, this mechanism developed by Peter Higgs, or at least developed fully by Peter Higgs, actually explains things. And 2 Nobel Prizes for actually building the instruments and 3 Nobel Prizes for the experimental or the theoretical work later, we realized that this electromagnetic force and this weak nuclear force are the same thing when you get to high enough temperatures. And so we've got this other period of the universe where we can now say we know what's going on, even though it's this incredibly dense, weird state, we can build particle accelerators that allow us to know what's going on. And we think, now think about that for a second. We've got this really disparate force between the weak force and the electromagnetic force, and we find out that they're actually the same thing. Maybe all of these forces are just low energy manifestations. It requires a universe that operates with exquisite rules. It has to be designed a certain way, because in this picture there's just pure energy at some point in time. And that energy decays in such a way that instead of always being exactly the same, or this incredibly homogeneous, identical situation, it decays, or as it cools down, it splits off, and you get this diversity of particles and forces that allow things like carbon to form, that allow things like water to form, that allow things like planets to form. It's really pretty remarkable when you think about it. And so as we push back, we think that there are, as you get eventually the strong nuclear force will become part of that. That's this grand unified theory. And eventually, maybe even gravity is subsumed into that. So you get this theory of everything. And even to explain it, as we're trying to explain all that, we realize that, wait a second, maybe there's this epoch where the universe, everything is expanding incredibly rapidly, and where it decays, now we get the universe that we see. So this is kind of the inflationary Big Bang picture. And here I kind of got it in terms of time, sort of. If you actually maybe maps it out a little bit more in time, please, you don't have to worry about reading all the stuff in there, except to say that it's really hot and things are much smaller down at the bottom, and as the universe expands, it gets cooler and lots of things happen. You've got inflation, you've got the Planck era, you've got grand unified theory, you've got the electroweak force, you've got quarks and hadrons, and you get hadrons splitting up, and then you've got the nucleosynthesis happening. Why I want to point all this out is just for this reason, that if we look at these areas here, these nice green arrows say something good's happening there. We've got lots of data of what's going on here. This is stuff where we actually know what's going on because we can measure it in the lab, and we've got theoretical calculations that back it up, and they agree very well with one another. But if you look at the bad, ominous red arrows, what you'll find is that there's actually very little to no data in these regions. And why that's important is, we want to continue to build stuff to push down into the earliest moments of the universe and see what's going on there. But there's this kind of odd gap right up in there where you go from the universe emits the cosmic microwave background radiation, where we've got a great deal of information. That's about 380,000 years. And we know that where that was emitted, again, just a little more background here, the reason why it's emitted is because before that time, the universe was hot enough that all the electrons, they may combine with protons, but immediately they get hit by photons and they scatter. And so these things are just scattered all around. Eventually, things cool off enough so that the collisions don't happen as frequently without as much energy. And so all the electrons become joined with protons. And what was this dense plasma now becomes neutral hydrogen, and all of those photons now just stream out to us. And we see them many years later as the cosmic microwave background radiation. Ultimately, they were emitted in the kind of visible ultraviolet region of light. They have now been redshifted by a factor of about 1,000 so that we see them as the cosmic microwave background radiation. But that's not the universe we observe today. In the universe we observe today, somewhere between about 380,000 years and 1 billion years, 3 really important things happen. We go from this uniform cosmic microwave background radiation to a universe that is teeming with galaxy stars and planets. And somewhere in that roughly 500 million years, 3 things happen. 1, all of those hydrogen atoms get reionized. So something happens to cause all of those hydrogen atoms to lose their electrons more or less permanently, because we live in a universe where everything is basically ionized out in space. We don't see hydrogen atoms floating out in space by and large. We see hydrogen ions, protons floating around out in space. What caused that were the second 2. The first stars formed. These are stars formed out of dominantly just the hydrogen and helium that were there. They don't have any of the extra elements in there. So what kind of stars are these? When were they formed? We know we call them population 3 stars. Population 1 are the ones that are forming and we see today. Population 2 were the generation before that seeded the population 1 stars. And then the population 3 were the ones that formed from this primordial hydrogen and helium universe, the first stars. But we don't know what they are. We haven't seen very many of them, if at all. We don't even have much indication that they may exist. So the question is, are they small? Are they big? What did they do? Did they contribute to the reionization or not? These are all questions that we just don't have. And stars form in the context of galaxies. And if you, I'll just go back here. You notice here on this slide it says that all happens about 400 million years ago, or about 400 million years after the Big Bang. 2 slides ago it happened 200 million years after though. We don't really exactly know the time scale of that either. It's somewhere in that range. And so this is where the James Webb comes in and says, the James Webb, among the other things it was built to do, is to go peer into this era and see what was going on. What do we know? We know that there are these fluctuations in the cosmic microwave background radiation. We know that we get galaxies out of that. What happened in that process in there? And when you understand that's what's being done, that helps give some sense to some of these latest claims that, ooh, Big Bang cosmology is all wrong. If you're a scientist, as we go peer in there, we kind of know that we're going to find some stuff that we don't expect. And I'm going to kind of highlight a couple of the things that we expect. Now, you notice how I've kind of laid things out. When we talked about Big Bang cosmology, that was the expansion of the universe, that we see stars and galaxies moving away. We look at the cosmic microwave background radiation. Notice that James Webb really doesn't have a lot to say about that we haven't already discovered. James Webb is still finding, lo and behold, the farther away a galaxy is, the farther away its redshift is. Doesn't have anything to do with cosmic microwave background radiation. Doesn't have anything to do with Big Bang nucleosynthesis. All of those things are the evidence pointing to the Big Bang. The big question is, can you get from that cosmic microwave background radiation era to the galaxies in a way that works? And the only way that James Webb could overturn Big Bang cosmology is to show that there's absolutely no way to do that. What it's likely going to show is that our simple ideas of how it worked are not sophisticated enough. So with that, there are 4 things that I see cosmology related that the James Webb can do. 1, how old is the universe? Not just its age, but maybe there's some new physics in here. You know, so we talk about the universe being 14 billion years old. I mean, how can I say we don't know the age of the universe when we made it to 13.8, I think it's 788 now or something like that. You know, how can we not know the age? Well, there's some interesting physics that shows up there. Understand galaxy formation and development, when they formed, what sizes, those sorts of things. David talked quite a bit about that in the previous talk. Finding the population 3 stars. And, you know, universe started, we're here to observe. It's kind of, James Webb actually has the capacity to weigh in on what's going on planets? What do we mean by habitable? Because it gives us some tools to explore exoplanets in a way that we really couldn't do consistently and reliably before. So let's kind of dig into those. Believe it or not, we have a pretty good idea. Well, we know that the universe is expanding. We've got pretty good handles on the expansion rate, but actually, though, as we're standing here today, there is this tension, and it's called the Hubble tension. I'm going to show a number of images over the next few slides, and they all come from one of these two papers. One's the Hubble tension, the evidence of new physics by Wang and Hu, or Hu and Wang. The other one is a Hubble tension and dark energy by Kamiankowski and Rees. And what it boils down to is we have two ways of measuring the Hubble constant. Hubble constant is a reflection of it's a measure of the expansion of the universe. And the way we originally did it, which we continue to do, is we basically go out and say, all right, how fast is something moving and how far away is it? So we measure a distance to something, we measure its velocity, and we calculate the Hubble constant. Now, to do that is a little complicated because to measure the distance is very, very hard. Measuring the velocity is actually pretty straightforward. You look for spectral lines that you know where they are, figure out where they're shifted, boom, you've got a velocity. That's easy, relatively speaking. Measuring distance is harder because distance depends, making something that measures distance is pretty hard. But we've got some tools that allow us to build what's called the cosmic distance ladder. You can go out and look at, there are certain objects that are close enough to us that we can actually, as we look at the object from one side of Earth's orbit, and then we look at it from the other side of the Earth's orbit, it moves on the sky. So knowing that triangle, you can figure out how far away it is. That's called parallax. There are other objects that we know their brightness depends on how quickly they pulse. They're regular pulsars, and the period tells you how bright they are. And so we can use parallax to calibrate these Cepheid variables, and that gives us a pretty good distance. Or now we've got a distance measure by some fairly bright objects. And then we can use these Cepheid variables. There's another kind of standard candle, which is a type 1a supernova, which is a supernova that happens almost the same way every time. And so as a result, when it goes off, it's kind of like a 100-watt light bulb. It's always the same brightness. But the problem is you got to be able to calibrate that. So we use the Cepheid variables to calibrate the type 1a supernova. And then from the type 1a supernova, we can see those very great distances. We can actually measure the type 1a supernova and the redshift. So we've built this cosmic distance ladder. And that gives us a value, or allows us to measure a Hubble constant. Now there's another way. We can go look very early in the universe, and that cosmic microwave background radiation allows us to measure various things that allow us to calculate a Hubble constant. Now, what's fascinating about that, and I'm not going to go into all the details, it's not like, well, we've got all these things, we can kind of podge it around and we say, okay, what's the best value of the Hubble constant? No, there's certain measurements we make of the cosmic microwave background radiation. Those constrain, given our just how physics works, how certain things happen. We adjust one parameter and then boom, once we do that, now we have the Hubble constant measured for all time. So we can measure it here in the early universe in a way that has one kind of free parameter. We set that free parameter, and then in that free parameter, you look on this graph here and you'll see that all of those kind of line up. Most of them line up right around about 66, 67, 68 kilometers per second per megaparsec. I'm going to get rid of the units because just realize they're always kilometers per second per megaparsec. But it's annoying to say that over and over and over, so I'm going to drop it. They all kind of line up right around 67, 68. So when we look at the early universe, we see it's about 68. Challenge is when we go out and look at the local universe, or where we are today, the late universe, we get measurements much closer to 73. Now, on this plot here, you'll notice that the bottom, there's this blue line that goes all the way across. That's the Planck result. That's the best measurement of the Hubble constant from the early universe. And the red line at the top is shoes, which is an acronym that I'm not going to remember right now, but it is our best measurement of the late time universe. And what you'll notice is that the Planck puts it about 67, Shoes puts it about 73, and their error bars do not overlap at all. And so this is the Hubble tension, because these ought to be the same thing. And what's interesting about that is that it's not like, well, you can just say, well, maybe we can throw in a parameter and make it fit. It's like there's no place in there where there's physics we can say, this is what we would introduce to make it work. There's no place for that. They ought to just match. So the fact that they don't is pretty disturbing. It's unsettling as a scientist to say, we think we have things understood. There's this tension that we need to resolve. And kind of the way it played out is that when we first started making these measurements roughly 20 years ago, both of them gave about 70. And as we started measuring them more and more and more precisely, they drifted apart. The CMB measurements turned it out to be lower, and the local distance ladder measurements turned out to be higher. So we need to get this resolved. So one of the things James Webb can do, because it can measure things with, it's got a bigger mirror than Hubble, it's got better sensitivity and resolution than Hubble, it can look at Cepheid variables that Hubble might have confused with, when you're looking at things, there's a Cepheid and then other stuff around it, it can resolve that better. And lo and behold, as it's gone through and done that, it's found that the past measurements we found of the local Hubble constant turned out to be correct. So it doesn't look like it's a systematic error, but perhaps it is it's a systematic error. And I want to put this a little bit in context, because when I was in college and graduate school, actually when I was in college, there was a fellow named Willie Fowler, who is a very famous, very well-known astrophysicist, who came and gave a talk at Iowa State. And he was talking about cosmology. And I remember him going through, he talked about a number of things, but the last little section of his talk was measuring the age of the universe. And he was talking about the Hubble constant, and he had this kind of novel technique of measuring the Hubble constant, which we thought was about 10 at the time. And he comes up, and his Hubble constant was 20. And I vividly remember his comment because it disturbed me. He goes, we know that everything else measures 10. My value is 20. It's within a factor of 2. That's pretty good enough. It's good enough for me. I'm like, how can you be wrong? That's just wrong. Something's got to be. What I failed to understand is that was just the precision with which we could measure things at the time. And there were two different techniques, over the next, in the 80s and 90s, there were two techniques. One gave a Hubble constant of 50 and one gave a Hubble constant of 100. That's why you got the two. One's 50, one was 20 and one was 10 for the billion years for the age of the universe. That was why one of the prime motivations for the Hubble Space Telescope is, what's going on here? Now notice where we're talking for the value here. We're talking 67, 74, kind of right in between those two. So let's see, that was 1988. We're 40-ish years later, and now we still have a tension, but instead of 50 and 100, we're now 67 to 73. So we made a lot of progress, even though there's still some questions here. But there is a question, is this just a problem with Cepheid calibration, or is there some other systematic effect? And it looks like there doesn't seem to be a systematic effect. But what we do need to do is we need to find some other way to resolve this tension. And maybe it's measuring Cepheids better. Maybe it's measuring the tip of the red giant branch. That's another standard candle that's brighter than Cepheids so that you can see them further away. Maybe you got quasar lensing, which is just looking, David Block was talking about that, where you got quasars that are lensed and you can use that to measure the Hubble constant, or megamasers, which none of these rely on, or these last two don't rely on the distance ladder, so maybe there's just a better measurement. The short answer as of right now is that it doesn't seem like there's any systematic effects that could account for this. And so this opens up the exciting possibility that maybe there's some new physics going on. Because, again, I want to emphasize this. Our determination of the Hubble constant using the cosmic microwave background doesn't have any other parameters that could say, well, maybe it's going to be higher later. Once you specify it here, it tells you what it will be later. It's one of the things that I really find cool about physics, is that there are certain places where it's just like, this determines what it is. And if it's different than that, it says you don't understand things. And so maybe we just don't understand things. And so physicists love this. This has been known for about 10 years. In the 10 years, there are hundreds of different models of how could we resolve this tension. Theoretical models. Now, mind you, there's not data that arbitrates this. But you see how much fun physicists have. It's like, ooh, we've got a problem here. Let's solve it. In fact, I remember being working over at UCLA full-time when the WMAP results came out. And I happened to be, one of my colleagues over there was on the WMAP team, one of the PIs on it. And so he was giving the talk, and I just remember the palpable tension. It's excitement about what's coming out here. And he gives a talk, and he basically came out and said, Big Bang cosmology is right. WMAP confirms all that we know. And there was a part of the reaction and a part of the reaction. Because the is, okay, we're on the right track, and the is, there's nothing new to look at here. So this stuff's fun for physicists. When you find stuff that doesn't work, it's like, ooh, that gives us new insight beyond what we know. One of the ideas that floats around out there is that it may be we find observational evidence that the Hubble constant, that what we're measuring as the Hubble constant actually changes over time. And so there's indications that that might be. Now, just to be real clear and explicit here, you notice that the tension reduction, it's some number there. I like that. The statistical significance of the one on the left is 2.1 sigma. As a general rule, if it's not 5 sigma, it's not a result. So this is indications, not data pointing to necessarily. So just bear that in mind there. So that's one place, because the James Webb, I guess I'll go back to that. James Webb has the capacity to peer into and investigate these with a different tool than we've used that hopefully will allow us to arbitrate some of what's going on there and see how do we resolve this Hubble tension. Another place where James Webb gets it is just being able to look at galaxy formation. Because of James Webb capability, particularly in the infrared, a lot of the lines that we look at to identify are the brighter lines that allow us to identify redshifts and see how far away things are. They tend to be in the visible ultraviolet. As you get further back in time, those get redshifted off into the infrared. That's why, one of the reasons why James Webb was built to see things in the infrared, is to be able to measure these sorts of lines. And what we found are galaxies going all the way back to a redshift of 14. Like I said, this is within the first 500 million years after the universe started. And the interesting result that came up out of that is that, as you know, James Webb's been observing for 1.5 years, 2 years now, not particularly a long time. You know, we're used to thinking of Hubble observations, which are 20 plus years worth of software and refining and analysis and everything. But even in these first things, there were galaxies being formed, or that we measured from being within the first 500 million years. That's in that era where all of that reionization, star formation, galaxy formation. So we're probing into that region in a way that we've never been able to do before. And what we're finding is galaxies, they found this particular paper, I think it's from 2023, so a little over a year ago, that there are 6 galaxies with masses of roughly 1 billion or 10 billion times the mass of our sun. One of these may be 10 to the 11 times the mass of the sun. And just for scale, our Milky Way galaxy is 10 to the 12 solar masses. Think about the implications of that. You've got to go from no galaxies, and within 1 billion years, you build something, or hundreds of millions of years, you build something that's almost Milky Way size. It's really hard to do that with just simple, straightforward models. It's hard. So this is one of those questions. It's like, okay, so we're now probing into this region. Our simple models of just this don't seem to be adequate. There must be something else going on. Maybe we're just seeing the very brightest ones, and that's skewing our perception of what's going on. That's a very real possibility. But as you're looking into something new, you would expect to find things that you don't expect. Either you can't see what you need to see to show that what you saw was unexpected. Well, that was a weird statement. But you get what I mean. we haven't seen everything we needed to see, so the thing that we did see looks weird. And it may be when we see everything that we can see, what we thought was weird actually is what we expect to see. That's a fun exercise. We ought to do that more frequently. Or it may be that what we're seeing is just that our simple models don't actually work. We need to build more complex models. But you'll find that as you look at the history, just even in my 40-ish years of being a physicist, there have been multiple times where we've had stars that were older than the age of the universe. Well, we knew that wasn't correct. We didn't say, ooh, Big Bang cosmology must be wrong. It's like, okay, so how do we resolve this? This is just another example of that. We found something we didn't expect. Okay, that means we need to probe it. The fact that we can now measure it now gives us tools to probe something and get more detail in that we couldn't get before. I just want to point out that reminds me a lot of how we study Scripture. And I don't want to step, if I'm out of line here, tell me. But what I find is that the basic picture of Scripture is in line. We know the basic story in there, but we've been studying Scripture for New Testament for 2,000 years, Old Testament longer than that. But yet, as theologians look in, there's still stuff. It's like, as you've got the bigger picture, you can now probe in, and every now and again, stuff comes up. It's like, oh, this is what's going on here. There's still interesting and fascinating stuff to discover. It doesn't change the big picture, but it gives us details that we didn't know before. So I find that parallel between that, which kind of makes sense if they're both God's revelation, if you think about it. So, as far as James Webb contributions, it provides data about galaxies, which we just didn't have before, and it helps us to connect the formation of the first stars to the developed galaxies. Hopefully, we'll be able to find some of those first stars, and maybe we're actually starting to. This is a paper published about 2 years ago, which found evidence that maybe some of these population 2 stars, and there's questions with these population 3 stars. Questions with these population 3 stars are, how large are they? Are they really massive? Are they more similar to our, well, if they're really massive, we're talking hundreds of times the mass of our sun. They could burn up in a few million years, 2 to 5 million years. That's kind of a blink of an eye in an astronomical time scale. And so this is just, we're going to be able to peer into this region and hopefully see some of these first stars. And I'm not going to say a whole lot about this because I think Hugh's going to cover it more later in his talk, so rather than be redundant there. But again, this is providing data about galaxies and stars which we didn't have before, and it's going to connect the dark ages to galaxy formation again. And one last thing I want to hit before I close is that the James Webb, because of how good it is, how much we've tamed the way the universe works to give us the information we want, we can actually find planets with this telescope. 2 different methods. One, where we can block out the light from the star and actually see the light from the planet. This is actually an image, again, one of the early images where where the star is there, and you can see in 4 different filters it has image of the light from the planet itself. When you get light from the planet itself, now you can actually determine what's going on with the planet as opposed to just saying it's there and how big it is. We can get spectra of atmospheres. This will give us information on what does it mean to be habitable. I mean, even just looking at WST 39b, this is a gas giant, hot gas giant planet. So take Jupiter, put it really close to the sun. That's the kind of planet this is. But we're finding silicon dioxide, we're finding methane, we're finding water, we're finding carbon dioxide, carbon monoxide. We can see these signatures in the spectra of these planets. And even if we go to K2-18b, I love the naming of astronomers. We are so creative at this point. Actually, there's a very good reason. I make jokes at it, but I know the names are actually very instructive when you understand what the names mean, or how they go about naming them. But here you see, you've got methane, you've got carbon dioxide, you've got dimethyl sulfide, carbon dioxide. We're getting information of what's going on inside the atmospheres, because so often we talk about habitable planets, but most of the time we don't even know whether there's water. I think it's fairly safe to say that before James Webb, when we're talking about Earth-sized planets, we don't have any idea whether there's even water in the atmosphere. And now we can actually start to probe that. The better instruments we get allows us to probe into that. And so I'm just really excited, not just because of the technological marvel that the James Webb is. But it really does give us this capacity to probe things about the universe that we had models of how it worked out, we had explanations for it, but there were explanations that seemed reasonable but aren't backed up by data. Now, especially in that region of the dark ages, where we're going from the cosmic microwave background radiation to we've got galaxies, we can now probe that region and actually have data of what's going on instead of just pretty good ideas. And it's going to confirm more and more, it confirms Big Bang cosmology, but it gives us a whole lot more detail on how did it all play out. And that's pretty exciting.